All right, if we're showing subspace, then we want to show that we've got a non-empty vector space and that it satisfies our conditions of closed under addition, closed under multiplication. So to show that it's not empty, we could say 0 plus 0 plus 0 equals 0, 0, 0, 0 is an element of R3, therefore non-empty. It doesn't have to be all zeros though. I could have just as easily picked 1, -1, 0, or 2, -1, -1. Any of those are elements of R3, and we've got a non-empty space. All right, so now we want to show that some vector u plus v, where u and v are elements of R3, and u plus v is also an element of R3, well, this would give us, let's call u x1, y1, z1. And u2, sorry, not u2, v, we could say x2, y2, z2. So we would need then our new values, x1, x2, y1, y2, z1, z2, to be equal to 0. Well, we know x1, y1, z1, and x2, y2, z2 are going to be equal to 0 because those are elements of our original subspace. So this is also true because 0 plus 0 would be 0. And these values, x1, x2, y1, y2, z1, z2, this is an element of R3. So closed under addition. And then if we look at ku, this would give us kx1, ky1, kz1, which would be kx1, ky1, kz1, which is k times x1, y1 plus z1. This is going to be 0. This is 0. This is an element of R3, so we're also closed under scalar multiplication. So also an element of R3, so it must be a subspace. All right. Now we want to know if this plane is a subspace of R3. So we're going to do the same thing. We're going to look at our vectors and determine whether we're closed under addition and closed under scalar multiplication. So first of all, it's non-empty. Again, we could have 0, 0, 0 as a point. So 2x, 3y, 4z equals 0 is not empty. 0, 0, 0 is an element of R3 and makes our equation true. So now let's look at taking our two vectors and adding them together. We know that 2x1, 3y1, 4z1 is equal to 0, and that we've got x1, y1, z1 as an element of R3. We could say the same thing for another point. All right, that's going to be true. And then if we added these together, it's also going to make 0. It's like I'm adding 0 plus 0. And we've got another point, x1 plus x2, y1 plus y2, z1 plus Z2, and that's also an element of R3, and it satisfies our initial condition, so we're closed under addition. Similarly, we could show, as we did above, that we're closed under multiplication. So, therefore, our plane is a subspace of R3. Notice this doesn't mean that we're going to cover all of R3, just a portion of R3.